Hello everyone, my name is Joshua Williams. For my final web GIS project, I developed a GIS suitability analysis for community planning in Haiti. The purpose of this project was to explore how GIS can be used not only to identify geographic hazards, but also to support decisions about where future resilient community development may be more appropriate. Haiti presents an important case study because communities throughout the country face overlapping geographic challenges. These include flooding, landslides, mountainous terrain, limited transportation redundancy, and highly concentrated patterns of development. Rather than looking at any of these factors individually, I wanted to create a GIS workflow that could evaluate several of them together. My primary analysis question was: which areas of Haiti demonstrate the greatest regional suitability for resilient community development based on landslide risk, flood risk, and road accessibility? An important distinction is that this project is a regional screening model. I'm not attempting to identify individual parcels where construction should occur. Instead, the purpose is to identify broader geographic areas that may warrant additional investigation for future planning. Data sources. To conduct the analysis, I incorporated four primary data sets. The first was the ICA Haiti flood risk dataset, which provides polygon data representing relative flood risk conditions across Haiti. For the suitability analysis, areas experienced lower flood risk or assigned higher suitability values. The second data set was the ICA Haiti landslide risk dataset. This was especially important because Haiti's mountainous topography creates a significant slope instability concerns, particularly for settlements, roads, and infrastructure. The third data set was a Haiti road network. Rather than treating roads simply as transportation features, I used proximity to roads as an accessibility variable. The basic assumption was the locations closer to existing transportation infrastructure would generally be more practical for development than extremely isolated locations. Finally, the Haiti national boundary was used to establish a study area and clip the analytical data sets. An Esri base map was also used to provide geographic context. I initially evaluated population data as another possible criterion. However, the available population layer was an internet tiled service rather than a featured dataset appropriate for the geoprocessing workflow. Rather than forcing an incompatible dataset into the model, I documented population as a limitation and an opportunity for future development. The next stage of the project involved preparing the data in ArcGIS Pro. Because several of the original datasets were online feature services, they first needed to be copied into the project's geodatabase. The flood risk, landslide risk, and transportation datasets were then clipped to the national boundary of Haiti. The analytical layers were projected into WGS 1984 UTM Zone 18 North. This was be this was important because I needed a projected coordinate system that would allow distance calculations to be performed consistently in meters. The flood and landslide polygon datasets were then converted into raster datasets. For transportation accessibility, I created a distance to roads raster. This produced a continuous surface representing how far each location is from the existing transportation network. Finally, each analytical criterion was reclassified into a common suitability scale. That step was necessary because flood risk, landslide risk, and road distance, excuse me, are originally represented using different measurements. Reclassification allowed them to be compared and combined within the same model. This section shows part of my ArcGIS workflow. Several geoprocessing tools were used throughout the project, including clipping, projection, feature to raster conversion, distance analysis, reclassification, raster calculations, raster to polygon conversion, and additional feature processing operations. I also used an ArcGIS Pro notebook to help organize and automate portions of the workflow. The important point here is that the final map wasn't created from a single data set. It is a result of several processing steps that transform different geographic variables into comparable analytical surfaces. Using the notebook also makes portions of the workflow more reproducible. Instead of relying entirely on manual repeating individual operations, GIS processing steps can be documented and executed programmatically. That becomes increasingly useful when a model needs to be updated with new data or adapted to another study area. Once the data sets were prepared, I created the final weighted suitability model. The model contains 3 criteria. Landslide risk received a weight of 40%. I gave landslide risk the greatest influence because Haiti's mountainous terrain creates significant constraints for settlements and transportation infrastructure. Flood risk received a weight of 35%. Flood exposure was given the second highest influence because many communities and transportation corridors occupy low-lying coastal areas, river valleys, and drainage systems. Finally, road accessibility received a weight of 25%. Road proximity matters because accessibility affects construction, emergency response, public services, transportation, and the long-term viability of new development. These weights are planning assumptions rather than universal values. A different planning organization could modify them depending on its priorities. The 3 classified raster layers were then combined using a weighted calculation. The resulting surface was classified into low, moderate, high, and very high development suitability. After producing the suitability surface, I extracted cells classified as high or very high suitability. Those cells were converted into polygons and evaluated by area. Small and highly fragmented polygons were removed so the final output would emphasize larger contiguous geographical areas. The resulting major candidate development zone represent regional planning opportunities identified by the model. Again, these should not be interpreted as locations where construction should immediately occur. They represent areas where the combination of the 3 variables suggests that more detailed investigation may be worthwhile. Looking at the resulting map, we can also see that suitability isn't distributed evenly throughout Haiti. Different parts of the country face different combinations of hazard exposure and accessibility. The spatial variation is exactly why GIS is useful for this type of planning problem. Once the desktop analysis was complete, I moved from ArcGIS Pro into the WebGIS portion of the project. I created a clean publishing map and prepared the analytical outputs for ArcGIS Online. The final suitability raster was converted into polygons so that the information could be delivered through a hosted feature service and interacted with more easily through a web application. I published several layers, including the resilient development suitability layer, the major candidate development zones, the Haiti road network, the Haiti national boundary, and a new layer called community planning observations. These layers were then incorporated into the Haiti Resilient Community Planning web map. This creates a connection between desktop spatial analysis and cloud-based GIS delivery. One feature that I specifically wanted to include was the ability for users to contribute information rather than simply view a map. For that purpose, I created an editable point feature class called Community Planning Observations. Users can document observations related to flooding, landslides, road access, drainage, water access, housing, public facilities, and environmental concerns. Additional attributes can store the planning concern, a recommended action, notes, observer information, and review status. This is different from simply drawing a point on a map. The observations become actual GIS features stored within the hosted feature layer. That means the application can potentially support an evolving dataset based on the information contributed by users. Experience Builder application. The final GIS component in the Haiti Resilient Community Planning Explorer, which I developed using ArcGIS Experience Builder. This brings the analytical layers and interactive tools into a single application. The application supports several capabilities. Users can search for addresses or named locations throughout Haiti. They can control which layers are displayed, use a legend to interpret the map, and apply filters to narrow the information shown. Users can also create and update community planning observations. Let me zoom out real quick so you can get a better look at this. The application also includes several spatial analysis tools. These include create buffers, find closest summarized nearby, and generate travel areas. For example, a planner could investigate features within a certain distance of a candidate development area or examine accessibility from a particular location. The goal was to move beyond producing a static cartographic product. Instead, the final output becomes an interactive decision support application where users can explore the results, conduct additional spatial analysis, and contribute information. Overall, the analysis identified clear geographic differences in regional development study. Suitability. Higher suitability areas generally occur where lower hazard exposure overlaps with stronger transportation accessibility. Conversely, areas experience combinations of flooding, landslide susceptibility, isolation, or other constraints generally receive lower suitability scores. The road network also illustrates the relationship between existing settlement patterns and transportation infrastructure. Road density was not treated as direct population measurement in this model. Instead, road proximity serves specifically as an accessibility indicator. The broader result is that development potential is geographically uneven across Haiti. Some areas offer stronger combinations of accessibility and lower modeled hazard exposure, while other areas face significant constraints. There are several important limitations to this analysis. First, this model is intended for regional screening. It does not currently incorporate detailed slope analysis, soil conditions, parcel ownership, population accessibility, protected areas, water availability, construction costs, existing building conditions, or community preferences. Those variables could substantially change the suitability of a location at the local level. Future versions of the model could incorporate digital elevation models, more detailed hydrologic modeling, population data, medical and educational facilities, land cover information, seismic conditions, and network-based travel time analysis. Most importantly, any candidate development zones identified through GIS would still require field verification, engineering analysis, and direct consultation with Haitian communities before an actual development recommendation could be made. GIS should support these decisions rather than replace them. To conclude, this project demonstrates how desktop GIS and web GIS can be integrated into a single planning workflow. I began with the independent hazard and transportation datasets. processed and analyzed them in ArcGIS Pro, created a weighted suitability model, published the analytical results through ArcGIS Online, and ultimately incorporated them into an interactive experience builder application. The final product does not simply answer the question of where hazard exists, it begins addressing a move forward looking question. Given what we know about hazards and accessibility, where should we investigate more closely when thinking about future resilient communities? Although this project focuses specifically on Haiti, the workflow itself is transferable. The same basic methodology could be adapted to other disaster prone regions by incorporating locally appropriate hazard infrastructure, environmental, and demographic data sets. Ultimately, GIS provides a framework for bringing those different forms of information together and turning geographic data into a tool for planning. I'd also like to acknowledge the ICA Haiti datasets and the Esri ArcGIS platform used throughout this project. Thank you for your time.